everyone, and welcome to this week's Joy of Abstraction book club. We're on chapter 13 this time, so that's very exciting. And soon we'll be moving on to the more technical category theory content. I will say that I am very tired today. Yesterday was the concert with the world premiere of my new song cycle for the Links project, and it really took it out of me. So I've been trying to wake up a bit today and drinking more coffee, but this is where we are. So this is where we're going to be. The first question today says, how do we pronounce these three-letter bold-faced category names, like group? I assume that group is not pronounced group. So I would just say group. If it's unpronounceable and it's obviously short for a word, I would say the word, like group. There are some others like ab. Ab is the category of abelian groups, and once I had defined it, I would call it ab. There's also mat, the category of matrices, and I would call that mat probably. Poset, if I've abbreviated it to PST, and someone the other day pointed out on Twitter that I am inconsistent, so sorry about that. But when poset is abbreviated to PST, I would indeed call it poset and not pst, although I would also be tempted to call it pst, but that's just what I'm like. Okay, next question. Is there some way of partitioning the category of monoids by binary relation to create an equivalence relation? I'm not sure what you're thinking of here, but later on we will see that the correct notion of sameness for categories is equivalence of categories, and that is an equivalence relation as indicated by the term equivalence. And there are a couple of types of equivalence that you can put on things. You can always look at isomorphism, right? You can always look at equality. So trivially, you can always put an equivalence relation on, which is equality, not necessarily very illuminating. Then there's isomorphism, and one of the things that we can show about isomorphisms in a category, oh wait, I've just realized we haven't done isomorphisms yet. Sorry, I was doing a mini course for math teachers at Math for America for the last 3 weeks, and we did isomorphism, so I got temporarily confused and thought I'd done it with you. Good question. Can we put an equivalence relation on these things? Well, what we're going to see in the very next chapter is that the correct notion of sameness inside a category is the concept of isomorphism. And so there is a concept of equality, and it's not that great. So isomorphism is better, and that does put an equivalence relation on objects which are sort of the same, count as the same inside a category. Categories themselves do form themselves into a category totality, but it turns out they're a bit higher dimensional than that. And so they form what is called a two category. And inside a two category, there's another form of sameness that is more subtle that you can put on, which is called equivalence. And that's also an equivalence relation. In some places, there's even more stuff, because there may be some things you want to count as an equivalence relation, but they aren't yet. And so there are techniques for kind of completing them into an equivalence relation. And so for monoids, we could trivially put an equivalence relation, a binary relation, on saying that using equality. We could do it using isomorphisms of monoids. So an isomorphism of monoids would be when basically there's a bijection of the underlying set where the bijection is also a morphism of monoids respecting the structure. And as they are one object categories, we might then ask ourselves what an equivalence of categories that have one object is. And we'll get to that when we look at equivalence of categories. And yes. So the next question is, can you have a monoid morphism from one monoid to another if the two monoids do not have the same binary operation? That's an interesting question, because I would say that no two monoids have the same binary operation unless they're the same monoid. But it depends what you mean by same. So for me, a binary operation, let me get the whiteboard up. Hello, whiteboard, my old friend. Sorry, that was about to become a Paul Simon joke. So for me, a binary operation on a set A is a function from A cross A, that's the set of ordered pairs, to A. So this is the set of ordered pairs of elements of A. So what would it mean? For me, it could only be the same binary operation if it's the same set and does the same thing. And the whole point of a monoid homomorphism is to be able to map from a monoid to a different monoid. So yes, you certainly can do it if they don't have the same binary operation, because the whole point, what did I say about monoid? Let me have a look. What did I say about monoid morphisms? This question did not come with a page reference, but what I said is, so maybe the confusion is that I've written the binary operation as circle in each case, but circle could represent anything. And so we could have a monoid A with binary operation circle, and we can map to a monoid B with binary operation star. And then the definition of monoid morphism would be the same, but just with a different symbol. And so then the definition of monoid morphism would be that f of, I called it x circle y, x circle y would have to equal f of x star f of y. So I hope that clears that up a little bit. Page 148. Does structure respecting or structure preserving mean it commutes with the operation on the objects? Let's see, where do I talk about structure preserving? In the case of monoids, structure preserving does mean that it commutes with the binary operation, that commutes with the operations on the objects, as long as you understand that to mean the right thing for commuting, which is to say that if you do the operation and then the function, it's the same as doing the function and then the operation. But you can have structure respecting, I suppose I don't need to be sharing right now. You can have structure respecting morphisms even when the structure in question isn't an operation. I suppose that's the point. So if it is an operation, then it's something that commutes with the operation, but it might not be an operation in the first place. Okay, so the next question, I do need the whiteboard back. The next question says, page 151, I'm having trouble with the last step. How does left multiplying both sides of the equation by this inverse go? So this is in the middle of page 151. Oh, I suppose I should have done this before doing the share. So let's make this a bit bigger. Here's the thing that we're talking about. And I'll go back to the share. So let's draw a line so we know we're starting a new thing here. The last step here, we're showing that f of the inverse is the inverse of f. So we're showing that f of the inverse is the inverse of f of x, where f is a group homomorphism. Group homomorphism. And the last step said we got as far as f of x circled with f of x inverse equals the identity. And then I said we're going to left multiply both sides of this equation by, so we're going to left multiply both sides by f of x inverse. So if we left multiply both sides by f of x inverse, then what we're doing here is we're putting that there, and we're also putting it here. So on the right hand side, we've only got the identity anyway, so we're just going to get f of x. Whoops. Inverse, right? So that's what we've multiplied by on both sides. And now those are inverses of each other. So that's going to become the identity. And so that means that what we get overall on the left-hand side is f of x inverse. And on the right-hand side, the inverse of f of x. So that's how we got to the last step there. I hope that that's a bit clearer now. Okay, next question. Page 153. Someone is wondering about the definition of order-preserving function. So the definition of order-preserving function, oh, that's purple. I wanted blue. Is that if x is less than or equal to y, then f of x is less than or equal to f of y. And the question says, I would not have guessed that this counts as order preserving. Could one interpretation be that this function preserves the existing order, but also adds additional order? I'm not quite sure where you're seeing it adding additional order here, because ordering, this is the ordering. It says that that x comes before y in this ordering. And what it says is that f has to respect that, so that after you've done f, the one that came before still has to be before. So it's as if these two were in line in a queue, and x was in front of y. I mean, there's an or equals, but I'm just ignoring that for a second. X was in front of y, and then when you move them, x still has to be in front of y. The result of where x ends up still has to be in front of y. Now, I'm wondering if the or equals is causing some confusion here. So that what that's saying is that they're allowed to land in the same spot. So even if x was strictly ahead of y, they are allowed to land in the same spot. If they were already in the same spot, then they always have to land in the same spot, because if x equals y, then f of x has to equal y. And so what it's saying is that they're not allowed to switch places. If x started off before y or in the same spot, the most that they're allowed to catch up to each other is to land on the same spot. They're not allowed to switch over completely. So that is order preserving. It's not putting any additional ordering in. It's just respecting the one that was already there. I hope that helps. So next question. Page 155. Can you say more about this set-based identity function being not order preserving? Page 155. So I think this was the situation where there are two different orderings on the same set. Three different orderings. So in the category of cosets, the three orderings make different cosets. This is true. And I understand this as the non-order preserving morphism between two objects. That is, it's not an identity arrow. No, because there is no, you can't have a non-order preserving morphism in the category of cosets. So in the category of cosets, any function between the underlying sets that is not order preserving just isn't in the category of cosets. It isn't there. And so I can only talk about the identity function not in the category of cosets. So what we've got here in this example, we had, first of all, the set A ordered by divisibility. Then there was the set A ordered by less than or equals, and the set A ordered by the number of factors. And so if we think about the identity function on A, it's only a function, right? The identity function, there's an identity in the category of posets that goes from A ordered like this to A ordered like that, the same thing. And similarly, when it's ordered by less than or equal to and thingy. And so the question said, is there a non-order preserving morphism from here to here? Non-order preserving. Now, I know what you mean, but in category theory, that's not what we would say. There is no, this is not a morphism in the category of posets. That's all. So outside of category theory, we can say that there is a function from A to A that does not respect the order, these particular orderings. There'd be no point talking about a function from this partially ordered set to that partially ordered set because it's not having anything to do with the ordering. You can think of it like that if you want to, as long as you're clear that that is not a morphism in the category of posets. Whereas there is an identity function like this in the category of sets, and then we can point out that it does not respect the ordering. Now, later on, when we do forgetful functors, we'll see that there is a way to relate the category of posets to the category of sets by a morphism of categories, which is called a functor. And what this does is it forgets the ordering. And what we're saying here is we're comparing the morphisms in here to the morphisms at the bottom. And we're saying that sometimes there is a morphism at the bottom that does not lift to a morphism over here. And so given you can look at the identity morphism here and observe that there isn't a way, there wasn't a way to lift it between those two. So there are a lot of, let me start again. There are a lot of different posets here that forget to the same set, but you can't necessarily lift every morphism from here to a morphism between the ones over there that live over it. And so this poset and that poset both live over the same set, so they forget, this is forgetful, they forget down to the same set. But you can't just take any old morphism down here and lift it back up to one up there if it doesn't respect the ordering. So that's what's going on there. Another question, page 161. Is there any instance where we would want to see the arrows for mat defined backwards from the way I define them? Oh yeah, so I define an arrow for matrices. I define an arrow from A to be an A cross an A by B matrix, but you could define them to be a B times A matrix. And what we'll see is that that's the dual category where you just, oh look, there's a giant patch of sun on my face. That's exciting. There's a dual category where you just regard all the arrows as going the other way. If I've just made the thing bigger so I can see where to sit so that the big giant patch of sun isn't right in my face. So yes, you can always regard the arrows going the other way and make a dual category. So the thing about the category of matrices is that I honestly can't remember what an A by B matrix is. I don't know whether A is the width and B is the height, or A is the number of rows and B is the number of columns, and whether or not that's the same thing, and which way anything goes. And so I confess that it's possible I just did it a different way around from what is standard, because I simply can't remember which way around it goes. And because I didn't want to get into the details, I put it the way around that would look more natural. But I didn't take into account that you might be very familiar with what an A by B matrix is. Because I was writing this for people who don't have any mathematical background, I wrote it the way around that would look more obvious, which is that A cross B is A going to B. So if you know which way around an A cross B matrix is, then you're welcome to do it the other way around. But in reality, in any given moment, one would define which way around it was. So one would say, specify which way around is A cross B, and then say which way around you're regarding the arrows to be. But it really doesn't make any difference. Okay, so the next question is, one of the points of matrices is to encode linear maps between vector spaces. I'm curious as to what are the other points of matrices. Well, I mean, a matrix is just a 2x2 grid, right? And 2x2 grids can be used for all sorts of things. And they can be used for other transformations other than linear maps between vector spaces. If you Google matrices, I just tried this. If you Google matrix, it turns out you get the movie, The Matrix. But if you Google matrices, you get the Wikipedia page for matrices, and it tells you all sorts of other ways in which matrices are used. Because all they're doing is that it's a 2x2 grid relating some things to some other things. And there are all sorts of uses of relating some things to some other things that are nothing to do with linear maps. And they pop up in graph theory, for example. You can encode the distance between different nodes, and they pop up. I understand that this is how something to do with how the Google algorithm works, where it's to do with the kind of number of times that different web pages mention each other. That may be extremely out of date, but that's one thing. People use it. So anytime you're relating two sets of data according to pointwise relationships, you can put that in a matrix, and it might be nothing to do with a vector space. Okay, I think that's the last question. So there's some praise. Someone is a graduate student and learned about this book on the panel on category theory outreach. Oh, I've got a big patch of sun in my face again. This time of year, there's a building right opposite my kitchen, and so most of the year the sun doesn't come in, and at this time of year it just peeks through at exactly this time in the afternoon. And I remember discovering this during COVID, that there's about 15 minutes when the sun is right in my face in the place where I make videos. So hello. So anyway, this person said that they really liked my duck characterization of the Untitled lemma. I'm glad about that, and is appreciative. Someone says, thanks for a beautiful book. And someone says, your desire to share and encourage the joy of abstraction is appreciated, respected, and valued. Thank you. Thank you very much. I'm sorry I'm a little low on energy today, but I hope that this helped. And I'm really glad that there's still you're still following along. So next time is going to be on, we're getting into the part on actual category theory now. So this is really exciting, and do keep sending in your questions. Thank you very much for being here and being interested. And thank you again to everyone at the Topos Institute for their support. And thank you for the sunshine for getting in my face. And let's see if I can find the off button now, despite the fact that the sunshine is in my face. And the answer is yes, I can. Bye.